But the number of free electrons per cubic meter is called n. So this is now the number of free electrons that passes per second through any cross-section. And each electron has a charge E. And so this is the current that will flow. The current, of course, is in this direction, but that's a detail. If I now substitute the drift velocity, which we have here, I substitute that in there, so then I find that the current, I get a E squared, a charge squared, I get N, I get tau, I get downstairs the mass of the electron, and then I get A times the electric field E, because I have here this electric field E. When you look at this here, that really depends only on the properties of my substance for a given temperature. And we give that a name. We call this sigma, which is called conductivity. Conductivity. If I calculate for copper the conductivity at room temperature, that's very easy, because I've given you what N is on the blackboard there, 10 to the 29. You know what tau is at room temperature, 3 times 10 to the minus 14. So for copper, at room temperature, you'll find about 10 to the 8th. You'll see more values for sigma later on during this course. This is in SI units. I can massage this a little further because E is V divided by L. And so I can write now that the current is that sigma times A times V divided by L. I can write it down a little bit differently. I can say V therefore equals L divided by sigma A times I. And now you're staring at Ohm's law, whether you like it or not, because this is what we call the resistance, capital R. We often write down rho for 1 over sigma, and rho is called the resistivity. So either one will do. So you can also write down, V equals IR, and this R then is either L divided by sigma A or L times rho. Let me make it a nicer rho divided by A. That's the same thing. The unit for resistance R is volts per ampere, but we call that ohm. And so the unit for R is ohm. And so if you want to know what the unit for rho and sigma is, that follows immediately from the equations. The unit for rho is then ohm meters. So we have derived the resistance here in terms of the dimensions, namely the length and the cross-section, but also in terms of the physics on an atomic scale, which all by itself is interesting. If you look at the resistance, you see it is proportional with the length of your wire through which you drive a current. Think of this as water trying to go through a pipe. If you make the pipe longer, the resistance goes up, so that's very intuitively pleasing. Notice that you have A downstairs. That means if the pipe is wider, larger cross-section, it's also easier for the current to flow. It's easier for the water to flow. So that's also quite pleasing. Ohm's law also often holds for insulators, which are not conductors, even though I have derived it here for conductors, which have these free electrons. And so now I want to make a comparison between very good conductors and very good insulators. So I'll start off with a chunk of material cross-sectional area A. Let's take it 1 millimeter by 1 millimeter. So A is 10 to the minus 6 square meters. So here I have a chunk of material, and the length of that material, L, is 1 meter. Put a potential difference over there, plus here and minus here. Current will start to flow in this direction. Electrons will flow in this direction. And the question now is, what is the resistance of this chunk of material? Well, very easy. You take these equations, you know, L and A. So if I tell you what sigma is, then you can immediately calculate what the resistance is. So let's take first a good conductor. Silver and gold and copper are very good conductors. They would have values for sigma 10 to the 8. We just calculated for copper. You've seen it in front of your own eyes. So that means rho would be 10 to the minus 8. It's 1 over sigma. And so in this particular case, since A is 10 to the minus 6, the resistance R is simply 10 to the 6 times rho, because L is 1 meter. So it's very easy. The resistance here, R, is 10 to the minus 2 ohms, 1/100th of an ohm. For this material, if it were copper. Let's now take a very good insulator. Glass is an example. Quartz, porcelain, very good insulators. Now sigma, the conductivity, is extremely low. They vary somewhere from 10 to the minus 12 to 10 to the minus 16. So rho now, the resistivity, something like 10 to the 12s to 10 to the plus 16s. And if I take 10 to the 14, just I have to grab a number, then you'll find that R now is 10 to the 20 ohms. A 1 with 20 zeros. That's an enormous resistance.